those that are absent.
Recording in progress.
All right. So just a reminder, because I know that every day you need a little dose of chem. So just a reminder, we will just be doing the tests for this unit, just the tests. All right. So kind of a reminder of what we've looked through. Can we have this handy dandy little packet? I am not a teacher that ever gives you a handout and it's like fill in the blank. I don't know. I think once you get to high school, that's just not my style of teaching. I don't want us to think this is a fill in the blank. I wanted to provide examples beyond what we are going to do. So what I definitely want to do as we're going is anything that's kind of highlighted, we will answer or fill in or whatever. Okay. So we talked about, we know soluble ionic solutes, and we are only held accountable for the always ions. So we said, for example, sodium chloride, we know it's completely soluble, and however much of the sodium chloride we add to solvent until it's beyond its saturation point, it will dissociate. And so in fact, if we would have a beaker of, let's say, 500 milliliters of water, if we would add 1 gram of sodium chloride, all of that 1 gram will dissociate into ions, and you won't visibly be able to see any undissolved sodium chloride solid. And if we would keep adding and adding and adding until we hit, we could say, the solubility, which is the maximum amount of dissolved solute that a certain amount of solvent can hold at a certain temperature. The way visually that we can confirm it is beyond the solute, well, that it's saturated, and the saturated will be holding the solubility value, a certain amount of solute per amount of solvent at that temperature. How we confirm it's saturated is you will see some undissolved solute. Now, we saw a little animation of sodium ions that we know will be surrounded by water molecules and so on, and chlorides, and how the majority of it are water molecules, and that it's not very often that these ions will collide, but they will collide. And so even though we write this as a single arrow, because we know a certain amount, even, saturated, very little are going to be finding each other, some do. And so we could write this as an equilibrium, even though we know so much that we'll be favoring right. I hope this, and then K will be much, greater than 1 usually. Okay. But we saw the other day the beautiful reaction. Let's see if I can remind us. The beautiful reaction of adding lead nitrate soluble to potassium iodide soluble, but the lead, whenever each lead ion could find 2 iodides, well, that created this gorgeous big bird yellow precipitate. And we say it is insoluble. But if we say insoluble means none of this, well, then we're being deceptive. Because we can measure, even if we call it insoluble, we can measure some dissociation. All right. And from that, then we can analyze equilibrium. All right. Can we look at this packet? So silver chromate. Now we are only responsible for knowing the always soluble. So you'll see when we start to do problems how the wording of the problem or other things that you are provided helps us ensure that we're treating it appropriately. Silver chromate. Well, silver. Aiden, what is the common ion charge for silver? Try again. Try again. Yes. And strangely enough, silver always shows +1. So silver, zinc, and cadmium are the kind of, I don't know, rascals of the D block that they don't alternate between a minimum of 2 different cation charges. Silver is always +1, zinc and cadmium always +2. So silver is +1. You're not expected to know chromate. Chromate is CrO4 with a -2 charge. So because of that, we know this should be Ag2 CrO4. Insoluble. However, we know a little bit of it will be existing as dissociated ions. Stephen, what should I write, including phase symbols, for the product side? Wonderful. Wonderful. If something is existing as an ion, we better write it. There's a huge difference between Ag without the positive charge and Ag with. As the ion and as the neutral element, very different species. So as AP students, we need to be on the top of our game with those details. And of course, being careful about the ion ratio. Absolutely perfect. And we need aqueous because they will be dissolved. Now, even though we say it's insoluble, if we start with the insoluble solid as reactant, and then the little bit of ions as the product, then the equilibrium expression gets this SP, solubility product. And as we work through examples today, you'll see like it makes sense that we call it that. So the KSP for silver chromate. Oh, by the way, we know we don't have to write the cation first. That's just usually like what we do, but you don't have to. Yes, sir.
So because it's not being divided, would that mean in the allocates, that means that it's generally incredibly small?
Yes. Yes. We'll look at examples. I think but crazy. Yeah, like it's good to know like in general what to expect in general. So we know, for example, strong acids, their Ka values are crazy big, crazy. We don't even like say a value because it's so crazy big. Where weak acids, we know 10 to the -3rd, 10 to the -5th, but we saw some that were 10 to the -10. So, I'd say generally 10 to the -5th. These in general, 10 to the -30th. I mean, 29 zeros and then a value as far as mole per liter. So that's why it's so okay that we're using that declaration of insoluble. Yeah, absolutely. Okay. Now, law of mass action. We were so fortunate the last 2 units. We know acid-base reactions are 1-to-1 mole ratio. So I have to be careful because we're going to have exponents other than 1. So for example, here, Ag will be raised to the 2nd. And we saw this the other day, of course, because solid is the reactant, then the reactant in the KSP expression just delivers a value of 1. Sure, I was going to say, so whenever, again, the insoluble solid is the reactant, and then the dissociated ions are the product, that equilibrium we call KSP, solubility product constant. So just like KAs, we know describe behavior of acids, and it will be hydronium times the conjugate base. And if it were a base, we know we'll get the conjugate acid and hydroxide. Well, we know if it's KSP, it'll be, shoot, the dissociated ions often not raised to just a power of 1 with a denominator of 1. All right. Solubility. I've referenced it several times, but to just like drive it home, I'm sorry for the fill in the blank. Please do not feel demeaned. All right. When we say solubility, we're talking about the amount of solute that's needed to deliver a saturated. Kyle, in your own words, what does that mean? Perfect. Match the amount that can be dissolved in that amount of solvent at that temperature. Yeah. Solubility can be conveyed in gram per liter, and that of course means grams of solute per liter of solvent, or mole per liter, mole of solute per liter of solvent. Okay, so KSP is unitless, like all our other Ks. We're just evaluating the value of it. Represents the equilibrium between the ionic solute and its saturated solution of ions. Okay, so let's dig into some examples. And I think this will bring to life, again, why we call it the solubility product constant. So on the second page in our unit packet, take a look. Our strong bases. So lithium hydroxide, sodium hydroxide, potassium hydroxide, calcium, strontium, barium. Those are strong because they're our only soluble hydroxides. Otherwise, oh my gosh, look at those. For example, iron 3 hydroxide, 37 zeros, and then a 5. So no wonder we call these insoluble, such a incredibly small amount of moles per liter dissolved. So when you say, can we expect them to be small? Yeah, go ahead, sir. Well, see, then I think like some of the sulfides, it's interesting. Sulfides are usually insoluble, but there is such a range. Look, -17 to -49. And that's a little crazy. I've seen -52. Oh, right there. Mercury 2 sulfide. Off the top of my head, that's all that I could, but again, like, holy crud. Whenever we express these concentrations, it would be crazy to express them as mole per liter. We usually express them in terms of part per million or part per billion. So for example, our tap water, when they are looking for lead ion or iron ion or mercury ion or nitrate ion, they're looking for, is there 1 nitrate per million water molecules? Are there, so yeah, these are minutes, really, really tiny. Someone saw, they tried with their calculator. I guess your calculator will not give you a value if you try to have it do, I don't know, I didn't try, I just believe them, like 1 to the -100th. Yeah, syntax error. Will it do to the -99? Yeah. So I guess there's like the smallest that'll, which again, like, oh my gosh, 0. I would. And I guess it won't, there's also a maximum. I think we won't do positive. Yeah, but I don't know. Anyway, silly calculator. See, our brains are so much better. So off the top of my head, I don't know, but that's, crazy. So usually like -30 is the common, I'd say, KSP value. All right, so let's look at a problem. And I hope that we see like, oh, not too bad. That's truly, in 10 minutes, that's where I hope our brains are really feeling like, oh, this isn't nearly what buffers presented us. Okay, sorry. No smiles when I say buffers. We're still like traumatized. I know. All right. Okay. Calculate the KSP value for bismuth sulfide given a solubility. All right. So we're asked for a KSP. Anytime we're given K values or asked for K values, we need our equilibrium reaction first. And if we're asked for KSP, that means our insoluble solid, Bi2S3. Okay. And in equilibrium, phase symbol's not required, but nice to have, in equilibrium with its dissociated ions. So 2 bismuths. What is the charge on bismuth in the compound? +3, perfect. How about sulfide? Yeah. Okay, be careful, be careful. It's just easy to make missteps. So our KSP will be the bismuth ion raised to the 2nd power and the sulfide ion raised to the 3rd. And that's what we're trying to find. All right, so we have our heading done. The solubility. Whenever we're given the solubility, that is in terms of the formula. They're telling us 1 × 10⁻15 moles of this per liter will be found at this temperature. But we realize that, oh, but for every 1 of these, I get 2 and then 3 ions. So we know we do an ice table. And just like water as a liquid didn't show, we don't do anything for our solid. We're not told we have anything else but the bismuth sulfide. So we assume, just like we did with acids and bases, if that's the only thing we had, that we're just putting this into the solvent and it has yet to dissociate. With insoluble solids, whatever you feel more comfortable with, we usually, for ice tables, for the change, use expressions in terms of X. It is up to you. Solubility is the value of X with insoluble solid equilibrium. But a lot of collegiate professors, some AP teachers, encourage the use not of X, but capital S to represent solubility. So it's up to you. We could keep calling it X, or if we want, we could just change things up because we're dealing with insoluble solids and call X S. It's totally up to you. But the solubility is the value of X. So our change, you could do it in terms of X or S, whichever makes more sense to you. We'll get the same thing either way. Okay, so it's either then that I have 2X and then 3X. We are given our solubility, so we're given our X. At this point, it's up to you too, where you want to go from here. I know a lot of students like, because we're given the solubility, to go ahead and plug this in here. And so they'll take 2 times 1 times 10 to the minus 15th molar, and then 3 times 1 times 10 to the minus 15th molar. And then plug those values in and then square and cube. Totally up to you. So what that would be then is 2 times 10 to the minus 15th molar squared times 3 times 10 to the minus 15th molar cubed. Or you could put in the expressions in terms of X. We could just algebraically simplify and say it'll be 4x squared and 27x cubed. And then this will be 10. Thank you, times x to the 5th. And then plug in x. It's totally up to you, as long as we're getting the correct answer, which is 1.1 times 10 to the negative 73rd. There we go. Oh. I know. Crazy. And we don't have to worry about units. Okay, so I was like, what we're doing to show, definitely our heading, ice, can use S or X. And then, you know, if you're gonna plug in your values and then get your answer, or do this and then get your answer. Yeah. Okay, so solubility product constant. Do we see the KSP is directly related to the solubility product? We're, you know, multiplying and taking to different powers. So I guess that's where our KSP designation came from. Okay. Next. Well, what if we're given KSP, but we want to find the solubility? So it's just the reverse. First, we would need our equilibria. KSP expression. Part of this problem. Sorry about that. All right, so we are looking for the solubility, which is X or S, whichever. Kyle, what do you choose? Do we want to do X or S? All right. We just assume that we don't have anything yet. And it will be plus 1x plus 2x. We're trying to find our X. The KSP. A lot of students feel, I don't know, it's a little unnerving that the coefficient of X is the exponent, but that's confirmation of the law of mass action in this case, right? So I divide by 4 and take the cube root, and our X, which is our solubility, here 3.3 times 10 to the minus 3rd. And we're solving, in essence, for the brackets. Go ahead, sir.
Extremely high K value for
Yeah, that is. Yeah, that's a pretty, so we would expect a higher value of solubility. So those will go hand in hand. Yeah, we're going to be all over the board. Like usually weak acids, again, like we kind of fall, -14 is usually our smallest because that would be KW. But here we have a big variety. Yeah, so -7 and then look, -73. Holy smokes. Go ahead, sir. What do you think? Why? So if we have well, let's see. So if we have HCl, I say aqueous. Okay, and now of course it's in general, right? And so let's say it's 1 molar. Well, would we say really in solution, this is pretty much 0. And then this is really the 1 molar and the 1 molar. And so the KSP, 1 molar, 1 molar, and then an incredibly small. And so I think we can expect greater than 1, right? It does. Oh, but then what if it's, 0.01? But still, this is going to be so small. So yeah, our numerator might not deliver just multiplying it, but yeah. Great thought. Unit on that. Yeah, you got it. Yeah. Oh my gosh, yes. Yep, absolutely. All right. What about this question? If we had 3 compounds and you were given the KSP for each, could we rank them in order of decreasing solubility? Can we just judge based upon the KSP value? And what would the relationship be? Can we say the greater the KSP value, if that's the product of ions raised to a certain power, the greater the KSP, the greater the solubility? So then, is the copper 2 sulfide the highest? So it would be first, and then the silver sulfide, and then the bismuth sulfide. There is an issue in just doing that. Yes. They all do not dissociate into the same number of ions. So therefore, we can't just judge solubility based upon KSP. But if they did have the same number of ions, so if we go back to the packet with the highlighted areas, so on page 1, part D, now, Silver chloride, you would be helped with that. AgCl, silver bromide, and silver iodide. Those are all silver halides. They all create one silver ion and one chloride ion, or sorry, one halide ion. So 2 ions plus 1 minus 1. So then we can directly. And so test what would have the highest solubility of the 3. You've got it. And then here, barium sulfate, calcium sulfate, lead 2 sulfate. Same number of ions, even though +2 and -2, still 2 ions. So here, calcium sulfate, highest KSP, highest solubility. So only if they have the same number of ions, because now we won't work through the math of this. If they have different numbers of ions, we would need to find S or find X to answer, because each solid dissociates into different number of ions. And actually, the bismuth sulfide, even though it's 10 to the negative 73rd, the solubility for that is 1 times 10 to the negative 15th, where the solubility of silver sulfide ends up being 5 times 10 to the negative 17th. I just solved for X. And then the copper 2 sulfide is 9.2 times 10 to the negative 23rd. So we can't judge. If they don't have the same number of ions, we would actually have to find our X value, or S or X. I know it sounds like I'm saying the same word or same letter. All right, so can we just entertain the next idea, and that will set us up for Monday? Questions? So how does solubility relate to KSP? If we know KSP, can we get solubility? And then how can we judge and rank solubility with KSPs? All right, common ion. We've heard that kind of concept before. If I have a beaker and we are asked to find the solubility of silver chromate. Silver chromate, if we put several scoops, it's going to lay on the bottom. But we know that some of that, even though we call it insoluble, will be doing its thing in a 0.1 molar solution of silver nitrate. Okay. Elena, anything stand out to you about AgNO3? When you put silver nitrate into water, what do we know it will do? Because that silver ion is paired with nitrate. It is going to completely dissociate. All nitrates are soluble. So guess what? We start with some silver ion. And that is where we'll pick up on Monday. I wish you a wonderful, wonderful weekend.